Good morning, everyone. My name is Boelo Schuur. I'm Scientific Vice President of the European Federation of Chemical Engineering, the EFCE. I'm a chemical engineer by training, and I received my degrees from the University of Groningen in the Netherlands, where after a master's degree in chemical engineering and a master's degree in chemical education, I obtained my PhD on a thesis about enantioselective liquid-liquid extraction. I built my career in academia, and since 2011, I've been working at the University of Twente, where currently I'm a full professor, and my chair is called Sustainable Separation Technology. I'm very happy to be involved in the introduction of this webinar on liquid-liquid extraction, which is at the core of my own scientific work as well. And specifically, this webinar is about liquid-liquid extraction, an essential technology in our energy and materials transition, from equilibrium measurements to process design. I'm looking forward to participate in it, and my role is to introduce the Spotlight Talks concept and the EFCE, which I will do now. To start with the Spotlight Talk series, this is the 6th year that we organized a series of Spotlight Talk sessions, and after the COVID pandemic, we have decided, based on the success of the sessions, to maintain the Spotlight Talks on the calendar, even though we are fully back to regular in-person meetings as well. And this year, from the 8th to the 10th of September, we have such in-person meeting with the European Conference on Chemical Engineering, the ECCE ECAP in Lisbon. Because of this European conference, there is only a spring sessions this year and no fall sessions, but in the even years, we also have sessions in the fall. This spring, we organized a total of 10 Spotlight Talks by 11 of our working parties and sections. We started with chemical engineering applied to medicine, and we have enjoyed Spotlight Talks from sustainability, chemical reaction engineering, process intensification, communication and classification, mechanics of particulate solids. Today, we can enjoy a session on fluid separation, and in the coming days, polymer reaction engineering, static electricity, crystallization, and early career chemical engineers will follow. We may enjoy these short sessions of 3 or 4 talks focused on specific topics by leading industrial and academic experts. The complete program is available on the EFCE website. You're encouraged to explore the remaining sessions as well, and in the near future, all of these Spotlight Talks will appear on the YouTube channel of the EFCE, where you can, if you miss them, still see all of them. The EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, and we represent more than 100,000 chemical engineers throughout Europe. The EFCE's working parties and sections cover all major specific aspects of chemical engineering and are the core of our organization. They form the scientific engine that drives all of our activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe, and in each of our working parties and sections, highly skilled engineers gather. I would like to invite all of you to have a look at the website, efce.info, to explore our scientific groups. Maybe you are interested in joining one of our sections. Joining a working party is only on invitation, but if you see that your country is underrepresented and you feel that you are a potential representative, or if you know a highly skilled individual in that domain of chemical engineering, please reach out to us and as well to your national member association. Before concluding, I would like to thank all of the people who have worked hard inside the working parties, the sections, and in the EFCE in general for this initiative to happen. Especially thanks to Martine Prof from Toulouse, who is doing most of the work related to all of these Spotlight Talks. And I thank Mark Hlawitschka from the Working Party on Fluid Separations, together with the German extraction community in the DGMA extraction Fachausschuss, who have organized together this Spotlight Talk. And I thank you for your attention. I wish the speakers of today and all of the attendees a successful webinar. I would like to give the word to Mark Hlawitschka, who is one of the liquid extraction experts in the Working Party on Fluid Separations, to introduce the webinar and the speakers. Mark, the floor is yours.
Yeah, thanks a lot for this kind introduction. So my name is Mark Hlawitschka. I'm full professor at the Johannes Kepler University in Linz for chemical process engineering since 2020. And one of our focus topics is the solvent extraction. Today, we will talk mainly about liquid-liquid extraction on different scales. So we have three interesting talks prepared for you. One is from the RWTH Aachen in Germany about accelerating extraction process development, holistic solvent screening, covering fluid dynamics. The second one is from our university here in Linz in Austria about the use of solvent extraction for the recycling of lithium-ion batteries. And the last one puts a little bit more the industrial viewpoint into this session. It's about conceptual approach for process development of liquid-liquid extraction by Borchardt from Raschig, GmbH. And finally, we will have some time for question and answer, but you are also allowed to ask questions using the Q&A throughout the session. Further on, I have to mention you are not able to speak, so please, for questions, use the Q&A. About solvent extraction, from my point of view, it's becoming more and more important again because it's one of the drivers towards climate change, but also due to the global political shifts that we see. So liquid extraction or solvent extraction is one of the core technologies for efficient purification, resource recovery, and recycling. And one of the main issues that we are facing here in Europe is the critical materials recovery, where we see lithium, cobalt, and nickel from the spent batteries, for example. But even so, if it comes to green energy, we need the rare earth elements, for example, for wind turbines, electric vehicles, and we see a broad application of solvent extraction towards pharmaceutical, hydrometallurgy, petrochemical refining, and wastewater treatment as well. So let's start with the webinar with the first talk about solvent screening for rapid process development from the RWTH Aachen by Lukas Polte. I just need to close mine. Oh, sorry. Now you should be able to open yours.
Now it should work and you should see my screen, right?
Yes, perfect. So the stage is yours.
Yes, thank you very much, Mark, for the kind introduction and the words. I'm very happy to be here and to give some insights on our experiences on process design and process development for extraction processes. And I fully agree on the points you said and just underline. So in the process developments we did in the research projects over the recent years for so-called next generations or sustainable processes, we usually face a unique challenge. So if you think about fermentation broths or metal recycling, enzymatic conversion, but also other recycling technologies, so hydrolysis, you often end up with an aqueous phase where our target products are very highly diluted in. And if you want to use, let's say, the classical petrochemical version of downstream processes, so rectification, this is not very sensible for those kind of product mixtures. And in the research projects we worked on, extraction, liquid extraction is often a very energy efficient alternative to tackle those challenges. And solvent screening is an essential part of the process development for extraction processes because the solvent screening and the solvent selection happens in a very early phase of the process development, but determines the process performance at the very end of the process development. And if I talk about extraction processes from now on, I refer to what you see in the middle here. So the combination of extraction and rectification. And extraction where product is extracted from a feed phase by a solvent, and the extract is afterwards treated in a rectification to one, purify our product, but also to enable the solvent recovery. And if you look at the literature, there is a bunch of different approaches for this solvent selection. The easiest one, just simply rely on distribution coefficients or heat of evaporation for the rectification part, so on simple performance indicators. You can go for more sophisticated models like pinch-based models, which depict the thermodynamic limitations very good, and give a very broad, let's say, picture on the thermodynamic feasibilities of separations. But those approaches have one in common: they're sequential. So in the phase of solvent selection, you do just those thermodynamic, let's say, picture of it, and the equipment design happens in a very later phase of the process development. Even if you go for flow sheet simulations and using equilibrium stage models in the phase of solvent selection, you will use constant HETS values, so height equivalence to a theoretical stage, which is perfectly fine for the rectification part, but which is not good for the extraction part. Because we know in extraction, fluid dynamic and dynamic effects and overall, they matter. So we see that, and we know from literature that the HETS value may vary by a factor of 5, 6, or even higher. Which means if you use the constant HETS value in this stage of process development, you will end up with not accurate estimated column dimensions. So the height will be wrong or not accurate, which also means you cannot accurately estimate investment costs at this point of process development. This is why we did set up, let's say, a holistic model-based solvent screening tool covering the whole process. Therefore, we need as input, for sure, our separation task. So the feed in volume, but also in composition, also the recovery we want to have for our target product, and the product purity we want to have after the rectification. Additionally, we need some property data, so pure component data like densities or viscosities, but also interfacial tension and information about the thermodynamics, binary interactions to predict the LLE, the BLE for both the separations. Knowing this input, we can then move to our process model, and the first thing in the extraction model is the submodel for fluid dynamics. So solving fluid dynamics within the extraction counterflow current column. And we cover here a few phenomena. The first one is we know extraction is about having a dispersion in the extraction column, but there's not only one drop. This is a droplet size distribution, which is represented by a Salter mean diameter. And we have a submodel predicting the Salter mean diameter based on the physical properties and also on operating conditions and the geometry of the column, which is trained on Salter mean diameters. So the effects of coalescence and breakage are lumped into this Salter mean diameter. Knowing the droplet size distribution, we can then calculate our sedimentation velocity. And since there's not only a few drops, but many of them, we have a certain interaction of the drops, so we need to account for swarm effects, which then gives us the final rising velocity of the droplets. Knowing the final sedimentation velocity, we can then calculate the hold-up, which is just the ratio of dispersed phase to continuous phase within our extraction column. By knowing the hold-up and also the rising velocity, we do know the interfacial area, which is present and available for mass transfer between the two phases, and also the residence time of both of our phases. And those phenomena, from a fluid dynamic point of view, also define our flooding capacity, which is the upper operation condition or boundary for our extraction column from a fluid dynamic point of view. All these phenomena are highly interlinked to each other, but they also depend on the column type and column geometry, which is why we implemented this model for 3 different column types, which is the pulsed tray, the rotating disc, and the Cuny extraction column, which all can be depicted by this model. Knowing now our residence time and the interfacial area for mass transfer, we can then move to the mass transfer model, which is kind of the core model of this extraction column model. And here we rely on a rate-based model, which is simply a differential equation along the height of the column. And the easiest form is just looking at the concentration of the product along the column height. So we have just one single differential equation. And then we defined our feed in composition. So we know the concentration at the top of the column. And also we defined our recovery which then gives us the raffinate concentration. And knowing those two boundaries gives us integration boundaries, which we can use to determine the height we need, so the column height we need to fulfill this separation task. In the next development steps of this overall holistic tool, we then implemented more ways to predict also other components, not only the product, but also to account for water and solvent, so the cross-solubility, but also as many solutes as you want to look at to have a multi-component mass transfer model within the rectification to be able to predict where other products and also the solvent and the feed will end up in the extract in the raffinate. Therefore, we also implemented another mass transfer model, which is the exact solution of the Maxwell-Stefan equations, which is capable of also taking into account the interactions of non-ideal fluxes in the mass transfer model. This is numerically very challenging, and if you're interested in that, for sure we can talk about that afterwards. In general, the easiest way, so just looking at the product, so just one differential equation is very fast. So this solves within not even a second. When you go to multi-component model for the mass transfer, this gets very numerically challenged and also time expensive. However, solving the differential equation for a product that defines our column height, as I just said. The fluid dynamics and define the flooding capacity, and that gives us the column diameter. And with those two, we did a full design of the extraction column. Also, we know from the extraction model the composition and the volume flow of the extract, which is then treated in the rectification column and the rectification model, which is kept simple because this is not the focus of our research. So we just applied shortcut models, Fenske-Underwood-Gudina, most of you will know it, complemented by some semi-empirical collation, which allows us also a full design, so giving the dimensions of the column, of the rectification column, and also the energy demand. With the full designed extraction and rectification columns, we can then move to our cost calculation. So the total cost account for investment cost of both columns based on the dimensions, and also the operating cost based on the energy demand. As I said, the feed flow is fixed, is given by the separation task, and we can then vary the solvent flow as an operating condition. And we can, by doing this variation, we can find our optimal operating point, optimal feed to solvent volume flow ratio with the lowest total cost. And we can run this model and this approach for as many solvents as we want to, and compare them by comparing the minimum total cost. By that, you getting a solvent ranking. And I want to show you some results on that for the case study of extracting acetone at 5.5% from water. On the left bottom side for a certain solvent, which is adiponitrile. And we can see some, let's say, typical things when looking at the cost categories. So at the left side, for very low feed to solvent ratios, again, feed flow is fixed. That means at this side, we have very, very high solvent flows, and the operating costs dominate. It is clear just due to the fact that we have a very high volume flow in extract, which needs to be evaporated within the rectification column. So there is a very high operating cost. You also can see that the investment costs at this point are slightly increasing. This is due to the fact that the columns get very large in diameter at this point. If we move to higher feed to solvent ratios, we see that the investment cost for the extraction are beginning to dominate. So the extraction column gets very, very large, very high, because here we are approaching the thermodynamical pinch, so the minimum solvent flow we can use to achieve the given separation task. If we look at some full screening results, here you see the results for, I think, the 20 best candidates from a screening of over 150 solvent candidates. And you see the cost categories given for operating costs and investment costs. And what you can see from this is that none of the cost categories itself is decisive, but you need to account for both to really get full picture of the performance of each solvent. When you look at the HETS values depicted for all solvents on the right y-axis, you can see that even for those top, let's say 10 or 12 candidates, even in this range, the HETS values varies by a factor of 3 from 0.4 to 1.2. So the thing we know from the literature, the indication that the HETS value varies by those factors is also validated with this model. Yeah. So to give a quick summary at this point, we can say we build up or set up a full predictive model. So we don't need to do any experiments at this point. And we only need some input parameters, which is our separation task and property data. And at this point for the data, we are linked to two data banks. So we are using the Dortmund data bank for pure component data. And we have two links to Cosmo RS and also to SMILES properties, which is an NN-based prediction of binary interactions from the colleagues from the ETH Zurich to predict our NTL parameters for our thermodynamic behavior. And we did see that by applying this process model or this holistic approach, we get really a full picture of the process performance or the process performance we will get up with in the end for both solvent and have a really comprehensive solvent screening and ranking. One thing I also want to mention is that this process model or the ranking you did see is not only, so there's another information inside because the function is also kind of a filter. Because if you think of solvents which might have very good thermodynamic properties, so very high distribution coefficients or low heat evaporations, they are also tested if they are feasible to be operated in an extraction column. So in this final ranking, they will not show up if they are just not operatable. So from a fluid dynamic point of view. And so with that, we could say we're done, right? Luckily not, because I always showed this process in the middle. And for sure, this is a simplification of process development and also of downstream processes for those tasks I talked about. The first question we always talk about so beyond the obvious is cross-solubilities. So every solvent has a certain cross-solubility with water, and for the solvent we can easily recover the let's say saturated solvent, and this can be used in the extraction column, but we will end up with a solvent loss in the refrigerant. So to really account for that, we need to apply another rectification column to recover our solvent. In most cases, this will be an azeotropic rectification to really get our solvent back. But in the real world, just the simplest cases, you only have one product. Mostly you will end up with byproducts and catalysts. So if you think of fermentation, you will have byproducts or substrates, and you want to know where will they end up and how to recover them. In which, with every additional component we're looking at, the downstream process will get more complicated. You will get another additional unit. And with every additional unit, the, let's say, design space for this process concept increases or grows exponentially. And from my point of view, for those more complicated separation tasks, the only answer to solvent screening is superstructure optimization. And if you look at, so now we have 3 columns, and if you look at more components, this will be 4 or 5 columns, and the extraction columns is just one of those 4 or 5 columns. And I already told you that really depicting multi-component mass transfer with an array-based model is very complicated numerically and will not be feasible to be used in a superstructure optimization or flow sheeting approach. This is why our idea was for those separation tasks to use our model, which depicts all phenomena in fluid dynamics and in kinetics, and to use a surrogate model for HETS prediction, which then can be coupled with superstructure optimization. And just as a quick idea how that works, I hope you can still see everything. how the surrogate model works. So we use our rate-based model, so the sophisticated model, to generate a database. So in the first step, we set up a sample, which consists of the property data and the separation task, and this together builds a feature set. With this feature set, we use our rate-based model to predict the column height divided by the number of theoretical stages. And by that, we get a feature set, we get the HETS value, and also whether this data point is valid. So in cases where the operation in an extraction column is not feasible, this will end up as an unvalid data point. We can then use this database to train two models. The first one is a classifier, which just says if based on an input set of property data and separation tasks, whether this is feasible in an extraction column or not. And the second one is a regressor, which then, in case of an invalid data point, tells us the actual HETS value for this input set. To set up this classifier and regressor, we use the knowledge discovery databases process, which we already use to build up some submodels for our sophisticated rate-based model. So for predicting sorter mean diameters and also sedimentation velocities, we use this machine learning approach, and it's very, let's say, very good for those kind of tasks. To be honest, for the regressor, mostly it ends up with an ANN, so an artificial network within hyperparameter optimization. And again, for the overall approach, this regressor can then be used because it's an ANN and it solves like directly no numerical time-intensive computations. And this can then be directly used as an HETS prediction coupled with equilibrium stage models inside of superstructure optimization or flow sheeting approaches. And just to show you some first results, on the left-hand side, you see the MAPE, so the mean average percentage error of the surrogate model over the number of data points. What I did not say is that we tried different sampling methods to build up these databases. This is based on an adaptive sampling approach. If you're interested in that, feel free to ask afterwards. What we see is that the prediction error, the percentage prediction error, gets to around 2%. So very, very, the model is very accurate at this point. And then if we also look at the parity plot, we see that most of the points are really lie in between this error of plus minus 10%. And if you think of the uncertainty we have in the original model, this is, I think, a pretty good, accuracy within this prediction. With that, I come to my summary and outlook. So the first thing we did see is that fluid dynamic and kinetic effects matter in extraction processes, and they do influence the solvent performance and thus the solvent screening. I want to emphasize that does not mean that we should take the best candidate from the solvent screening. It just gives an idea. So the first 10 solvents from the ranking, we know if we use them for further evaluation, so we go to the experiments afterwards, which are very time and cost intensive, they will not end up in the end with a bad performance. For all of those solvents in the ranking, let's say in the first 20 candidates, they will always end up at a good performance at the end of the process development. Then we implemented two different multi-component mass transfer models. I didn't show that, but they both have a very high accuracy, even if they are full predictive. And we used this sophisticated model to build up a database and a surrogate model for fast and robust prediction of HETS values. So let's say this is the outcome of our work, to be honest, because this also will be published and everyone can use it. And just as simple, you need only your property data, your geometry, and then you can predict HETS values, which is very good, I think. And this model, the surrogate model, we now will use for an application to a solvent screening case study, and just as shared for the holistic approach. We will also extend our approach with a rectification body method for the rectification part and an automated column sequencing part for the extract and raffinate, which goes into the direction of superstructure optimization. And last but not least, we will use the surrogate model for transfer learning on experimental data to even increase the accuracy of this model. With that, I want to thank you for your attention, and I'm happy to answer any questions.
Thanks a lot, Lukas. So you still have the possibility to ask questions using the Q&A. That's a question mark at your Zoom, actually at the bottom in my case. So please use that one. I will use the time a little bit to introduce you again, Lukas, because I did not do this at the beginning. So Lukas is at the RWTH Aachen, at the chair of fluid process engineering of Professor Jupke. I think he is in the 4th or close to the 5th year. And so I think he's pretty at the end of his PhD. I'm not sure where your path is going to, but if there is someone interested, I think he or she can come in contact with you, which might be beneficial every time.
Yeah, thanks. I didn't think of introducing,
So we have some time to wait for questions. There are no questions till now. So everything is clear. So it was a quite nice talk. I prepared at least one question to start. If you have the whole model finally, so mini plant experiments are still an issue or are still done in industry to check out what happens. Is it possible to couple your model finally towards the experiments to get something like a digital twin to check and optimize it online, for example?
Yeah, for sure. So the simple model for sure. Also the multi-component mass transfer model, I think with some more additions or let's say changes will be applicable to digital twin or process control and optimization. But I think, and Daniel Borchardt will have more experience on that. For the operation, there you even need to be more precise in predicting or covering the fluid dynamics. So for APS, advanced process control, my approach would be to use a population balanced model to really account for coalitions and breakage inside of the extraction column, because I think the changes in fluid dynamics and also flooding capacities, you really need to be precise in the prediction of that, which is not that important for the solvent screening part.
Yeah. You talked about machine learning, for example. There is a pathway towards physical-based machine learning. So what are you using? Because there's still, if you're in industry, the question, can we really use machine learning and trust it finally? Or how can we use finally the results? What's your pathway?
Yeah, that's a good question. So I think a very good approach is to use physical informed neural networks. So if you have for APS, for process control, if you have some, let's say, material balance equations which need to be fulfilled, you can build up a machine learning architecture, so neural network, which incorporates those equations, right? For our prediction for the surrogate model, we went another way. So we use artificial substance systems for the database. So we cover a whole range of input parameters, let's say, so that afterwards in the usage of the surrogate model, we only do interpolation, because those ANNs are very good in interpolating. So it all depends on the database you use for the surrogate model, for the machine learning model. And if that is broad enough and you only do interpolation, I think they are very trustable, to be honest.
We got an online question here. Dear Lukas, thank you for your interesting talk. I usually use Kremser equation for estimating number of stages for extraction column. Did you compare your model results with Kremser equation? How close or different are the results?
Yes. So the Conceptual equation is to estimate the theoretical number of stages, right? And our model does not calculate number of theoretical stages because we have this rate-based approach. But we use different equations, so stage model, equilibrium stage model, Conceptual equation, and also a graphical method to evaluate the number of theoretical stages in post-processing. So our model just gives us the column height, and to get an HETS value, we need to divide this column height by the number of stages. And therefore, we also use, for example, the Kremser equation. And if you're in the range of low concentrations for your product, what I did see is that graphical method and also the full stage equilibrium stage model, they are very close to Kremser equation when you have a low cross solubility. In case you get to high cross solubilities, this may deviate by, I will not say like 20%, but that would be the first guess on my side for that. Yeah.
Okay, thanks a lot. So if you have your tool, did you try that one even so in industrial case, or did you have own experiments from your laboratory, for example? Did you have the chance to build up an extraction column, distillation column, compare it there directly?
The data, that would be very, very nice. So
Yeah.
we have an extraction column, and our extraction model is validated against experiments we did, and also all experiments we found in literature. So we did use this data, and we have there an RMSD. I think it is about 0.9%. That's the range for the data we were looking at. The rectification model, honestly, I don't know how accurate that is. Would be very nice to at least at a point validate the whole process, but for now there is no data available.
Okay.
Yeah, it's also very expensive to do like technical scale experiments for rectification and extraction. You need a lot of solvent system, and yeah, that's very, very expensive.
Yeah, for sure. Okay, so we are pretty close to the end of your session. So thanks a lot for this talk, for answering all the questions. But please stay here because all of the participants have the chance to even ask questions that we might answer at the end, or you might answer them directly in the chat.
Yeah.
That's even so possible.
Yeah, thank you very much, Mark.
So we come to the second talk. I just need to switch, which is from our house here from Johannes Kepler University, Linz in Austria. It's about the use of solvent extraction for the recycling of lithium-ion batteries. Alexander Keller is a postdoc at my institute here, Institute of Process or Chemical Process Engineering, even so. And he is looking at solvent extraction of lithium-ion batteries since more than 5 years right now, and has there a long background in analyzing, but even so in operating different columns, but even so looks at the whole recycling process. So Alexander, the stage is yours. I just have to close my session again, and then you can open yours.
Yeah, thank you, Mark, for your kind introduction. Today
now we see it. Perfect.
Okay, thank you for the nice introduction. Today I want to talk about the solvent extraction or liquid extraction within the recycling of lithium-ion batteries process. And today I want to show you 2 different case studies. First of all, I want to go into some detail about the recovery of excess sulfuric acid. And the second case study is the extraction of manganese, cobalt, and nickel. So the classic approach in the recycling process. So maybe you're not too familiar with the recycling process of lithium-ion batteries. So I want to show this to you. If we have the spent lithium-ion batteries, they come from a wide range of different applications. Consumer electronics, electric vehicles, and energy storage are the 3 major sources of the spent batteries. And if we go to an hydrolytical process, then we start typically with a discharging of the batteries to avoid short circuits, minimization of fires, and mechanical processing. And as they are discharged, we continue with the mechanical treatment, so shredding, classifying, and sorting. And here we already start with the recovery of different fractions, so aluminium, copper, steel from the housing, collector foils. And what's of interest in our case is the so-called black mass. It's the active material of the lithium-ion batteries. So here are the value materials, lithium, cobalt, and nickel. And to get them separated, we continue with the hydrometallurgical treatment. So first of all, with the leaching, here we dissolve the metal oxides in acid, and then we continue with the purification. So typically we find there side elements like aluminium, iron, copper in a small quantity, which is not suitable anymore for recovery. And in the last step, we continue with the raw material extraction. So as you see here on the slide, the leaching is proceed at a high acid concentration. So typically with a pH value of smaller than 0, typically -1 or something like that. And the purification is typically carried out the pH value of 3 to 6. So you see we have there a huge pH shift, and this will be an issue I want to show you in the next slides. So again, here the black material, the cathode active material. Here we have the different elements, lithium, cobalt, manganese. And from the anode side, there we have also graphite and silicon, which could also affect the extraction in the downstream process. So the case study 1 is the recovery of excess sulfuric acid. So typically, if you want to purify the leachate, you do this by precipitation. So we start with the leachate solution where lithium, cobalt, iron, nickel, aluminium, and manganese are present, and we want to get rid of typically of aluminium and iron. And we do this by precipitation of the hydroxides. And this is typically in the range of pH 3 to 6.5. And to do so, we have to get rid of the excess sulfuric acid. So this is typically very chemical. We need lots of chemicals. So typically in the range of, for 1 kilogram of sulfuric acid, half a kilo of, we need there caustic soda and the same range of calcium carbonate. So here we have a high chemical requirement of chemicals on one hand, and the second one is that we also produce a lot of waste. And here we got an idea, maybe we can use solvent extraction to minimize the chemical requirement. And here the idea was maybe we can use an anion ion exchanger so that we can extract the sulfate to the organic phase so that the leachate become acid-free, as the amine will emit hydroxide ions. And then we can take the organic phase, strip that, and recover the sulfuric acid. And the organic phase we can reuse for new leachate. And then we have not a production of waste in terms of sodium sulfate. And yeah, you can use also the sulfuric acid in the further process. So maybe for the leaching process again, or maybe another case for the stripping in the extraction later on. Yeah, we did some experiments with trioctyl amine, which we dissolved in shell salt D70, and used here phase modifier because trioctyl amine tends to build up a third phase, and to avoid this, we use this phase modifier. But we saw with the investigated phase modifier, we have no influence in the extraction yields, which was very beneficial. Yeah, we carried out some experiments and we could achieve extraction of the sulfuric acid of already 98%. And what is also of interest is after the stripping, the obtained sulfuric acid, it's on the right-hand side of the right-hand graph, stripping, there we are also interested in the purity of the obtained sulfuric acid, and then we saw that we have low concentrations of aluminium and cobalt in the stripping or in this stripping solution. And this is also right now a point where we do some research to minimize the co-extraction of the metals so that we can use this for the stripping in the extraction process. So an idea where we can apply the acid recovery in the overall process is depicted here. So between the leaching process and the purification process, So between the leaching process and the purification process, we can apply the acid recovery. And the recovered sulfuric acid, we can either use for the leaching process, and there we have the requirement that we have a high concentration of sulfuric acid, but the purity is not too important. Or we have maybe a lower concentration of the sulfuric acid, but a higher purity. In this case, we can use this recovered sulfuric acid for the stripping process in the solvent extraction process later on. The second case study I want to show you is the extraction of manganese, cobalt, and nickel. So typical hydrometallurgical approach to separate these metals from spent lithium-ion batteries. And there, typically, we start with the choice of the right extractant. The two most dominant extractants are deeper, so this is phosphoric acid ester, and there we see that that deeper extract or prefers to extract manganese over cobalt and nickel. So we see here is a good choice for the extraction of manganese, but yeah, in the second case, we could also extract cobalt or separate cobalt from nickel. But as we see here from the isotherms, that this is a pretty hard job to do. Yeah, on the other hand, there is Sinex 272, which is developed for the separation of cobalt and nickel. There we see that this is a really good extractant for this separation, but we see also that the separation of manganese and cobalt is not too good. So we have to, for our process, we have first to extract the manganese, and secondly, the cobalt, and the third step, the nickel product. Yeah. Yeah, if we want to go, right now we had a look on the equilibrium aspects, and for the extraction or for the continuous extraction, maybe in an extraction column, it's also of interest how we can manage the pH value during the process. One possibility is to add directly sodium hydroxide to our to the feed, but this has a major drawback as cobalt can precipitate as a hydroxide, and then we have trouble to dissolve this again. So a better way is to neutralize the deeper in the first place, and then we don't have anymore the pH shift during the extraction. So now the question arises, how much should the deeper be neutralized? And this is depending on the neutralization degree. We see or which affects the equilibrium pH. So we are able to shift the pH value. Typically during the extraction, the pH will shift to the acidic range, but with higher neutralization degrees, we can compensate this pH shift. So in the best way, we do not change the pH value during the extraction, but maybe also our feed is too acidic, then we are also able to shift the pH value to a higher pH value, which is beneficial for the extraction. Yeah, and this we took for the further investigation for the continuous extraction, and we investigated the extraction on a pulse disk and donut column, which is depicted here. And first of all, we did experiments for the separation of manganese and cobalt, only focusing on the operation parameters, which is the phase ratio, the loading of the column, and the pulsation intensity. The very first thing what you do in this setup is you have a focus on the hydrodynamics, and here I want to show you some insights about the hydrodynamics, especially on the holdup. So what we are interested in the extraction process is small droplets, because we have there a high interfacial area. On the other hand, typically also a high residence time in the column, so we can also achieve the equilibrium conditions. What you see here is with the pulsation intensity, we can manipulate the droplet size itself and also then the holdup. So we start from the very low pulsation intensity with the mixer settler, go on to this dispersion regime. We have already small droplets, and continue to the emulsion regime, which is not too beneficial, as the droplets become there very small and we are near to the starting point. Yeah. So let's have a look on the extraction yield. So we did here, what I want to show you here is a design of experiments where we had a look on the pulsation intensity, column loading, and phase ratio. And what we obtained in the first place was we saw that we have no significant effect of the column loading in the range of 12 to 24 meters per hour, which is a typical operation mode. So we continued that, and then we saw, okay, all of these effects, we have a second order effect of the pulsation intensity as well as the phase ratio. And with that, we could produce a nice model for the extraction yield as depicted here. So we, by manipulating these parameters, we could already obtain there an extraction yield of more than 95%. Yeah, to further enhance the extraction yield, we then had a look on the effect of neutralized deeper, what I want to show you here. And what I want to highlight here is if we have no neutralized deeper, so the pure native deeper, then you see here in this graph on the left, here on the left, this is the feed concentration. And we see that the extraction yield, or the remaining manganese concentration, decreases with the column height, which we expect. But we see that this extraction yield is limited due to the pH value inside the column. So with continuing extraction, the pH value becomes lower and lower, and hence the equilibrium will be shifted to the educt side. So we are limited in the extraction. To avoid this, we use this neutralized deeper And here, with a higher neutralization degree, we see that this effect of the limited extraction due to the pH value becomes lower and lower with increasing neutralization, or sometimes also called saponification. So maybe you would say, okay, I use the highest neutralization degree, but you have also to have a look on the side effects. And here I want to show you some findings in our research. With a higher neutralization degree, you see also that the interfacial tension becomes very low, which means that on the bottom of our extraction column where the neutralized deeper is present, we have a very low interfacial tension, which leads to an emulsion regime. And maybe also we are then close to the flooding point. Although in the upper part of the extraction column, we will see a Mixer-Settler regime because of the high interfacial tension. So by applying this neutralized deeper, you have also to have this in mind. Not that you operate your column on the flooding point and you couldn't operate this properly. What you also see here is some aspects about the pH value. As we have here on the lower part of the column, a high concentration of neutralized deeper, you would also see that lots of protons will be accepted from the organic phase, which means that you have on the lower part of the column a high pH value, which leads to a co-extraction cobalt. And what you also would see is as the droplets rising in the column, they will face a lower pH value, and there you will see that the cobalt will be scrubbed within the extraction column, and so the organic phase will purified already in this extraction column. And so that you have on the top of the column a higher concentration or higher purity of your product. With that, I want to come to my conclusion. So what I wanted to show you is that there is a wide range of applications of solvent extraction within the recycling of lithium-ion batteries. So one hand, we have this traditional separation of value materials, manganese, cobalt, and nickel, but also we have new methods to recover excess sulfuric acid. Typically we start with the equilibrium studies as a basis. So on one hand, we choose the extractant, the correct one, also get an idea of the pH value, which is required for the operation. And then in the continuous extraction, we want to simulate the industrial process and focus more also on the purity of our final product. With that, the end of my presentation. I want to thank you for your attention, and I'm open for questions.
Thanks a lot, Alexander. So you are still allowed to ask questions. We have 56 people right now online in addition to the presenters. I'm pretty sure there might be some questions now or even later on. So please feel free to ask. I will start with a starting question, actually. So we had a talk about simulation modeling. Why didn't you use just modeling to describe your recovery process?
If you have a look on the extraction of manganese and cobalt, the simulation is a good starting point to choose, for example, the height of the extraction column and also the operation mode. But if we go to the industrial approach, then we are interested in in purity, for example. So we are interested not only to okay, we come to the range of 95% of extraction yield or purity. There we are interested in 99.9% or 99%. And their simulation is not capable to cover this aspect. So there we have to do the experiments to reach this high purity and the requirements of the industry. So simulation is a good starting point, but you have to do the experiments to be really sure that your extraction column is working and your process is working well and robust.
Maybe you can add some aspects. So if you're talking about high purity, you even need to measure these high purities. So how do you do that?
Yeah, there are different techniques. Typically at our institute, we use ICP OES for the elementary analysis, and for equilibrium studies, for example, there we measure the concentration of the metals in the feed concentration and in the raffinate typically, but we have also here the possibility to directly measure the extract, so the organic phase. There we are right now doing experiments that we can directly measure the concentration, because here we have sometimes problems with the resolution. So imagine you're interested in the extraction of manganese from cobalt, and you have only maybe 10 milligrams per liter of manganese, but 1 gram per liter of cobalt. And if you have there only 1% extraction of cobalt, maybe you will not see this directly by mass balance, because the section or the limit in the resolution of the ICP OES is maybe about 5%. So there it's crucial to measure the extract directly. So this is right now a research we do. Otherwise, you have to go another way. So you have to strip the organic phase and then have a look on the aqueous phase, on the stripping phase. But you have all the time to assume that all of your metals from the organic phase will go to the stripping solution. This is not all the time the case. So it's known, for example, for aluminium, that's really likely in the organic phase. There's a strong bonding to the deeper. So, for example, there you couldn't be sure that all of the metals are detected with this technique. So it's better to measure the extract directly.
Okay. There is one question. Perfect. Hello, Alexander. My question is about the use of saponified D2-EPA in pulse column tests. You mentioned a lower interfacial tension when increasing saponification degree. Did you observe any separation difficulty in the settler for these specific tests?
That's a good question. So what we see is that on the bottom of the extraction column, there we have this high saponification degree or neutralization degree. There we were faced with the emulsion regime, but as the droplets are rising, the saponification degree decreases. So at the very top of the column, we have more or less no saponification anymore in the deeper anymore. So there we had just the same separation like with untreated deeper. It was a really nice separation.
Okay, thanks a lot. We'll wait just for a further question, if there's one or not.
So maybe one additional remark there. What could be an issue is that if you are too close to or too high saponification, that could lead to entrainment, so that droplets will go with the raffinate. So you have to be aware of this.
When we think about D2EPA and Cyanics that you also use, these go back some tens of years. Why isn't there a distinct direction towards new extraction solvents or other solvents, maybe? Do you have any idea? Why are we still using them?
Yeah, I guess they are well applied, or they're cost effective. So maybe Cyanics, yeah, but there are also some competitors already there. But yeah, if you go to, if you want to make money with this, maybe you try to have a look to already to processes which are well applied, and then maybe you just change the feed, and then you have not to face too much changes anymore or uncertainties.
Yeah. So there are some solvents in development phase, but I think quite early.
Yeah, for example, ionic liquids are also of interest in the research. There we have also to have a look to which development step we are. So this typically ionic liquids, they are used in the lab scale, but also you have to think about different other aspects. So toxicity, for example, or how you can get rid of them or clean the columns and stuff like that.
Yeah. Okay, then we will switch to the third talk. So thank you, Alexander, for your talk. There's another question. Perfect. That's one we will still account. Hello, Alexander. Thank you for your nice presentation. Do you use model or artificial systems or real samples during your experiments? If you use artificial systems, do you expect any other impurities may affect the results? Second question, does the type of lithium oxide affect the extraction efficiency?
So right now we didn't use artificial intelligence, although it's really
Well,
interesting.
it's about artificial systems. So if you made up your composition by your own, or if you got the real samples from some
we obtained some differences, not regarding cobalt, nickel, manganese, and the stuff, but for example, the silicon from the black material. There we saw that sometimes we are faced with crud formation, and this is not was never a problem with artificial solutions, and we think that or believe that this is due to the silicium in the black mass, which accumulates in the column, and there we saw then a crud formation. Yeah, that was a big difference between the artificial solutions and the real solution.
So you use both. And the second question is, or was, does the type of lithium oxide affect the extraction efficiency? Do you have any idea about that?
The lithium oxide. So we did also some experiments about the leaching process. So, but there we only focused on the operation of the leaching process. So the reaction temperature, the residence time or reaction time, the ratio of the black mass to the liquid, also the concentration of sulfuric acid. But there we only focused on one type of black mass. So I couldn't give you unfortunately, an answer.
Okay. Then we will switch to our next talk, and we will have even time later on to discuss further questions. So our next talk is from Daniel Borchardt. I just need to open my slide again. Just a second.
Okay.
It's about conceptual approach for process development of liquid extraction. And as you can see by the affiliation, it's an industrial relevant talk now. And Daniel, we have a long cooperation. When I was back in Kaiserslautern, we were together in different topics about solvent extraction. So he developed to an expert for Raschig about solvent extraction, and I'm quite happy to have you here today.
Yeah, thanks for the kind introduction. First of all, good morning to the audience. So I would also kindly introduce myself. My name is Daniel Borchardt. I'm working for Raschig since 10 years as a process engineer in the application field of gas-liquid and liquid-liquid separation, with the main expertise in liquid extraction and phase separation. And thanks for the invite, having a spotlight talk here at the EFCE. And also thanks to my customer who is giving me the approval and the green lights, sharing some findings, some investigations we made during a process phase that took us 4 years, that can illustrate the conceptual approach for process development of a liquid extraction process from an industrial point of view. So I will shortly introduce the agenda, start with the requirement of the technical concept, dive into the process description, then share some general information about the conceptual approach for the process development in the liquid extraction, go into the process optimization. So we have a process that is yielding quality optimized. There's a very strong interaction between the thermodynamics and the hydrodynamics. And based on our findings, we made an apparatus selection for the extraction process. Afterwards, we're executing some pilot trials for the scale-up to a commercial plant. And then I will close the presentation with a short summary.
Share the slides again.
I do share the slides again. Okay.
They might be gone.
Let me see. Second screen. No, I cannot share the screen again. Can you see something on my screen?
No, not now.
Can you allow it to share something? Maybe that is...
It must be allowed. There's no open.
So unfortunately, I cannot share anything right now.
Not, I try to share it again and close it again. Maybe it got somewhere. Well, can you try it again?
Yeah. So somehow it is not working right now. What a pity.
You see the green arrow down there?
Yeah, I can see it, but
if you click it, then nothing happens.
No. So we were testing it in the beginning, but now it's not working again. Shall I get out and call in again?
Maybe you have to get out and get in again. That might be the easiest way. So if you have any further question for the first 2 talks, we can use the time right now to answer some of them. Hello back.
So now it is working.
Perfect.
So can you now see my screen?
Yeah, now we see slide 3.
Awesome. Okay.
Perfect.
Sorry for that. So about the requirement of the technical concept, it's a chemical recycling process of plastic waste to chemicals. So it's matching with the main focus on this webinar, a technology in the transition towards sustainable energy. We have some key points. So it's a multi-component system and organic feed. And during the first lab scale test, we investigated that the water content in the solvent is leading into a yield optimization. We got an industrial scale from the customer with 50 kTA, so 7 tons per hour feed. And also the larger scale is under investigation future-wise. Some challenging tasks I would like to share. It's the selective isolation of a target component that I cannot specify here. It's under non-disclosure. Reaching a specification in the product and also required yield is optimized and maximized. And we also considered solvent recovery. About the process, it's a Conti process of chemical recycling plastic waste to chemicals. So the first process step is the reactive pretreatment to remove impurities, subsequently entering into a pre-wash column from remove potential entrained unwanted components from the upstream process. Furthermore, this washing step should increase the robustness of the overall process as we have different feedstocks or feedstock qualities to consider. Then we get to the core process, the selective extraction process or solvent extraction process to selective isolate our transfer component, and afterwards using a scrubber or a back extraction to removal of the residual portion of the solvent entrained in the raffinate due to a high mutual solubility between the solvent and the feed phase. And on the downstream side, we have a fractionated treatment of the extract produced during the solvent extraction, separating different organic components that we call byproducts, and the water flow contaminated with the solvent is then emitted from the last stage of the fractionation supplied to the regeneration column to recover or recirculate the water and solvent to the different process steps. The pre-wash, the solvent, is the extraction, solvent extraction, and the back extraction. About the general conceptual approach for process development, we do separate it in a way between the design of experiments and the scale-up data. So first of all, we start with the process requirement. So that's the solvent selection and the solvent generation. Could already be a showstopper if the solvent generation could not take place. Then we have the hydrodynamics, for example, the physical data. So the driving force of the extraction is the density difference between the continuous and the displace phase, as this defines the hydrodynamic limits with respect to the specific capacity. That's why we call it throughput capacity. The greater the difference, the higher the specific capacity. In addition, the viscosity could also be a limited factor, for example, as we can maybe with a high viscosity only get operated with a limited selection of installations, for example, sieve trays, pulsed, rotated installations. And also very important as a physical data is the drop size distribution. So the surface tension or interfacial tension can severely limit the specific capacity that can be realized. So small surface tensions also in favor for formation of very fine droplets, which then would be occur unwanted entrainment in the system. Then we have the coalescence behavior. Or very often happens that we have any wreck formation or mold formation between the interface. The internals that we would choose, also based on the material choice. So waterability characteristic is very important for choosing the right internals. And of course, the dispersion direction or mass transfer direction. And this is always in line with the thermodynamics. For example, the distribution equilibrium that gives us an idea about the effort we have to put in the system, especially the phase ratio that we have to consider getting to a small concentration range. We have the reaction equilibrium, some mass transfer events that could take place in the column as soon as the feed is getting in contact with the solvent. And of course, also the solvent circuit, especially preloading that could harm the distribution equilibrium. So this box can get supported by operating a mini plant. We did it for this project, but unfortunately the time schedule would get exceeded. As soon as the specification is reached, we would get to the scale-up data. So we would select the right apparatus for this separation task in the liquid extraction. We have different apparatuses available. For example, a pack column with structured packings or random packings. We have a sieve tray column with a downcomer available. And for this choice, we would then investigate Very important scale-up data, that's the flooding point, so the maximum capacity, the nominal load at 75 to 80%, and the partial load that could have an influence also on the HETS if you would reduce the specific capacity. Of course, the efficiency that has to be in line with the hydrodynamics, and the yield and process stability. And based on these data that we would generate, we are getting to the industrial scale or demo scale to generate the technical mass balance of the individual apparatuses, including the return flows, to provide the design of the apparatus. So the dimensions like the diameter, the requested height, the diameter of the decanter, of different nozzles that are required for operating the plants, that is then containing in the engineering data sheets. I would like to dive into the solvent or the core process, the solvent extraction process. The selection of the solvent to be used for the extraction process was made using the infinite dilution activity coefficient and the associated selectivity for the individual transfer component that I cannot share. As I said, it's a multi-component system considering a cut, keeping a specific group of components in the extract, leaving at the bottom of the column for the downstream fractionation process, and the other components that are leaving in the column on the top of the column as a raffinate that are necessary to contain in the product. But this was provided by the customer, so we knew that what solvent we have to use for the process. A typical first investigation is the distribution equilibrium. So we are contacting the feed material with the fresh solvent, mix it, transferring this into the separation funnel, using different analytical methods like GC, FED, GCMS, ICP-OAS to investigate the concentration range in the extract or raffinate and extract to get to the determination of the distribution coefficient that we can now then draw into this equilibrium diagram as a curve that gives us a first idea or an initial conclusion that then could get drawn concerning the difficulty of the separation. And as flatter the curve, the higher the amount of theoretical stages needed, and the minimum solvent ratio to reach the specification or the end concentration of the product. So we noticed as we were conducting the first lab scale test that the water content can improve the yields. So we were adding more water, conducting these trials batch-wise and subsequently to see what is the impact. And as you see right here, the black equilibrium curve is no water in the solvent, and the green equilibrium curve is a very high amount of water in the solvent. In the end, in addition to the specification that we have to reach for the transfer component in the product, one overarching goal is to keep the yield as high as possible. So the loss of feed should kept to a minimum, since the achievable product quality relatively to the feed quality is a key factor for the economical efficiency of the overall process. So we had to find a suitable working range. By adding more water in the solvent, a significant increase of yield can be observed. We want to minimize the risk that by process fluctuations, for example, if you operate the process and you would just use a bit less water, that could harm the overall process. So on the other hand, we could see that a pretty high amount of water, the curves approach an asymptotic threshold value. So there's no longer any relationship between the efficiency losses and the presumed growth that we would gain in yield. And therefore, we also have to consider that the expenditure is getting higher by adding water to reach the target specification. So we had to find out what amount of solvent we should use for getting into the low concentration range. So we were ending up in a suitable working range that is here, in the red line. So that would be the working range we would consider for operating the plant. but we had to investigate the number of theoretical stages needed to meet the specification. So we made the first assumption using equal solvent to feed ratio of 1:1. Noticed that the specification could not get reached. We have feed concentration that is more or less the same. Then trying to reduce the working line or to get it a bit deeper, getting into the low concentration range, we noticed that we could reach the target specification, but we would like to generate a bit more buffer for operating a bit more robust the columns. So we get to a number of theoretical stages that is 8, and then increase the phase ratio to see that there is enough space between the target specification with a number of stages between 9 and 10. So we used this information that we conducted with shaking tests, small shaking, lab scale shaking tests. We know that the amount of, or the number of stages is 9 to 10. We have a pretty moderate phase ratio, so we could generate sufficient hold up in the column. There is a high quantity shift caused by the mutual solubility, and the density difference for this extraction column was higher than 250 kilogram per cubic meter. Also, the low interfacial tension was leading that we do not need any pulsation, and also the dynamic viscosity for selecting the right dispersion direction was in the range of water. So especially because we had to choose, or we had to consider a wide operation range that is required because we have different feedstock qualities. One of the feedstock is a bit more dirty, the other one is less dirty. We decided that the typical application for this area would be a packed column filled with a structure packing, considering also a material choice. And I was preparing one slide why this is so important to choose the right material. We have here a short or a small apparatus that we were building up here in our technical center. It's made by borosilicate glass. We can add the liquid from the bottom, from the top. We first mix the solvent and the feed for equilibrium conditions. Under ambient conditions, we could also heat it up, but then we had to use a covered glass. And we can test a plastic material, for example, that's the Raschig ring, ceramic materials like a structured packing, or the metal packing, structured or random. And what we can see here on the left-hand side, that's an organic dispersed system by using a plastic ring. And as you can see that there's a very high wetting characteristic. So they are leading into a building in streaks. So the specific surface for the mass transfer would get very low. So that would not be suitable for an organic dispersed system. And on the other side, that is a picture of the aqueous dispersed system with a very low wetting. As you can see, there's a nice droplet formation, so no wettability available, or a medium wettability. And this would be suitable or applicable for a water dispersed system. So it's very important before you start by executing pilot trials to investigate the wettability characteristic for the real substance system. After this was done, we were building up a column filled with a structured packing and also random packing. So that's the extraction column on the left-hand side, and that's the scrubber column on the right-hand side. It's a DN50 borosilicate glass column, jacketed, that we can keep the temperature constant over the entire column height. We were building it up with an effective height of 5 meters. We have exchangeable dispersed phase distributors for the top and for the bottom in case we would change the dispersion direction. We also take some samples. So we have a profile sample points over the entire column height that we can track also the HETS, or what is necessary for the scale up for the industrial scale. And we have some heat exchanger for all inlet flows. We do consider some mechanical components, for example, gear pumps. We are a fan of gear pumps or using gear pumps for executing the trials, as it is more like a pulsation-free feeding. We have an interface level probe that is located in the top or bottom decanter, depending on the disperse direction. And that is sending a radio signal to a transmitter, keeping the valve open or closed to keep the interface at the same level. And we also consider a pulsation that is available, that is a PTFE below, located in the bottom decanter, moving up and down, same what Alexander was sharing before, that we can set the amplitude and frequency in a range to get a smaller droplet size distribution. That is generating just an additional degree of freedom for any system adaptations, especially for substance systems with a medium to a high interfacial tension. And that's a packing we use, for example, a ceramic packing or a plastic ring, depending on the dispersion direction that is needed for the process. That is a hydraulic that we investigated by operating the pilot trials. I cannot specify the capacity, but we could notice that as higher the ratio, the volumetric ratio between the solvent and the feed, so as higher the solvent ratio, that was expected, as higher also the capacity, and especially by using water at a specific amount, we could also increase the flooding point or the maximum capacity. So the orange line is the maximum load and the blue line is the nominal load. And we used this information in the end, these pilot trials, to found the basis for the scale up. So we normally need 3 points, that is the maximum capacity, the flooding point, the nominal load capacity, because we normally set our design point between 70 to 80%. And we also consider the top and sum conditions, especially for systems and technical systems with a high mutual solubility. There is like a graph or curve or profile of specific capacity along the column height. Could be that as soon as the feed is getting in contact with the solvent, that the specific capacity is higher in the bottom or in the top of the column, that we have to consider for the dimension of the commercial plant. And also the HETS values plus the scale-up factor, that is something, that is already published, how to generate a scale-up factor, but we also have our company internal empirical function to get from the pilot trials or scale-up trials to the final design for the commercial plant. So our customer is getting the diameter, the required height of the active section, also the decanter size and manhole size for the installation of internals, also the measurement equipment for the interface in the bottom or the top. And in the end, that's the outcome for this project. We could successfully start up the MDU. So that's a picture of the overall process. I was just picking out the extraction process, but we were successfully in operation and on spec in the end. So last year in the third quarter, the column was built up, and we are happy that the overall system is working as it should be. And a short summary, there should always be an intense investigation of the thermodynamics and the hydrodynamics relationship to reduce the amount of pilot trials. And we normally need 3 scalar parameters, so the flooding point, the max capacity, the nominal load, for also the partial load. If there's any influence for operating the plant not at 80%, and the HETS, including the scale-up factor, to get to the required height of the industrial scale. And in the end, the MDU, the industrial scale, was successfully in operation on spec. So, many thanks for your attention.
Thanks a lot for your nice talk. So you are still allowed to ask questions, so feel free to write in the Q&A some questions. Only with questions you can learn something about or from the speakers at least. But we have later on even some time. Oh, perfectly. There's one question. Hello, Daniel. Thank you very much for the very interesting presentation. Could you please elaborate on the parameters that led you to choose a structured packing column instead of a conventional sieve tray column? Additionally, could you describe your strategy for calculating the actual tray height from the theoretical height?
Yeah, there is one characteristic for structured packings or packed columns, that is the operation range. So we can get down to a very low specific capacity that would normally not be possible with the sieve tray column. To be very honest, that is maybe something that we will share in the next meeting. We also use the sieve tray column, but not for the extraction process, for the back extraction process, because we were struggling a bit getting into a droplet size distribution that is in a range we normally consider. So the droplet size distribution we were in favor with is between 2.5 to 3 millimeters. So we were considering also operating a sieve tray column that is pulsed with a downcomer. But for the wide operation range in the extraction, the structure or the use of a structured packing is in favor for us. Yeah. But that is also published that the operation range for structured packing is even more wider as for sieve tray column. Yeah. And the second question was about the height, right?
Yeah, it was your strategy for calculating the actual tray height from the theoretical height.
That's something that we cannot share. Sorry.
Okay. So you need to contact Raschig directly.
Correct. Yeah, we can support
Get
you.
an advice. So you showed some pictures from your own lab, for example. You have some columns, DN50, 60, don't know exactly the size.
Yeah.
Do you scale up directly from DN60 towards the large scale size that you showed on your picture latest?
Yes. Yeah, it's sometimes a bit difficult if you use a plastic ring, for example, because in DN50 you just get a few inside, and that's why we would like to get to at least DN50. But the sieve tray column we are operating is in DN100. That we can scale up from this diameter. And we also have a mini plan, for example, pretty complex to investigate the thermodynamic behavior.
Yeah.
So, but that's something I would then, if I get the green lights again from a customer, share in the future. Maybe here in this webinar for the European Federation of Chemical Engineering, or maybe next year at the DECHEMA meeting. Yeah.
Okay. When we're talking about DN100 column, that's quite a large diameter for universities, actually. So we had some in Kaiserslautern back, but we still have some stored here. But when I calculate the amount of liquid solvents I need for them, do you do mass transfer, or are you only doing hydrodynamic studies?
Hydrodynamic studies. We try our best to investigate thermodynamics with a very low quantities in a mini plant, for example, to use this information to operate the plants just for the hydrodynamic investigations. As you said, one IBC is done in 5 hours if you use, for example, a DN100 or DN80. So, and especially if you use real substance systems, hazardous goods, for example, you need to be very careful. So we try our best to reduce the amount of trials by investigating the close relationship between thermodynamics and hydrodynamics.
Just checking if there's another question. So from your experience, you have, I don't know, 10 years of experience right now in solvent extraction. I'm not sure exactly how much.
7 years.
But what were the main pitfalls you were observing? So when we look at distillation, there are some recommendation books, main pitfalls for distillation columns. I'm not too sure if there's one for extraction. Might be a choice.
That's also a book. Yeah, I would exceed the time schedule today, but what we investigated, if you put something on a paper to say that's the right mass transfer direction, it was what we investigated very often the case that mass transfer events are leading into the wrong decision. So also for this process, we started by using the expected mass transfer direction in the droplet was not correct, because we had a very high oscillation of droplets, for example, as we were distributing the solvent phase, and this was leading into a very high emulsion. So we would not be even able to operate the plant by just choosing this direction. So we had to change it to feed disperse. And that's something you wouldn't see by just operating a lab scale test. So you have to operate it in a column. That's why it is so necessary to operate these tests and scale-up trials in a DN50 or DN100 column, because you can just see these events more clearly in this scale. So that's very important.
There might be another question. Do you expect a big increase of the HETS between DN50 tests and the industrial scale due to increasing backmixing effects of the diameter?
That can happen, but what we experienced, so we are getting up to a maximum diameter of 2 meters. That was possible. So that was the biggest column we were scaling up. We know that there are effects of backmixing, but that's something we consider in our scale up. But I cannot tell you how we do consider this. So, but yeah, indeed, there is an influence.
Yeah. So you have some internal insights how to account for that. You mentioned several times the disperser. So you have some dispersion unit actually. And when I was looking some 10, 15 years ago towards solvent extraction, we had some dispersing units, but I wasn't never sure if you really need it, because there's a mixing typically if you have some internals like the Kühne column, they're mixing in the first 5 compartments and it might affect the flooding finally. So the occurrence of flooding. So when do you use dispersion units, or do you adapt them, or do you have one size, one design for everything?
No, we do have different. So as I said before, we try to keep the velocity in the hole to 0.3 meters per second and the diameter to 2.5 to 3 millimeters. As we increasing the specific capacity, we also have to change the disperse phase, the distributor, as the amount of holes need to increase to keep the speed at the same level. But especially for structure packings, you equalize it as soon as the droplets are entering into the structure packing. So I would say that it is not the biggest priority to keep it always in the same range. But what we also do differ to other companies, if you use the structure packing, some companies are installing a distributor plate in between. So they're using a structure packing, then a distributor, a structure packing distributor. But for us, it is not the philosophy, because we pack it through, because otherwise you are cutting your capacity. So you have a big advantage using a structure packing with a high specific capacity, reducing the diameter. So you are it's cost intensive, to build up the column. So you have to keep it as small as possible. And if you use a redistributor, you would cut your capacity and you have to build it up a bit larger. So that's why what we experienced, we can easily pack it through until 20 meters. That is absolutely fine.
Okay. When you have the chance to ask a little bit further questions. Let's wait. There's someone. Olo, do you have a question?
No, I was actually also wondering. Usually they say from the N100 upwards, you can easily scale, but apparently within your company you have already a way to go from the N50. No, I wanted to say that maybe also if you still have questions for Alexander or Lukas, we could slowly start to wrap up this spotlight talk. So Alexander and Lukas, could you come on the screen as well to close down the session? If there are any questions for one of the speakers, then please let us know.
I am here, but my computer's free, so I need to jump on the phone. But yeah, I'm still here for some questions.
So Daniel, I just have a quick question for you. You were talking at the beginning about plastic waste recycling, and we have even some insights, not about solvent extraction plastic recycling, but about the pre-streaming, I would say, of the plastics. And there is a huge variation of the plastics you get typically. Is that a huge problem for the solvent extraction finally, because you don't know exactly your feed stream?
Yeah, but that's why we're including the pre-treatment, that I cannot share what pre-treatment. But I can share a link that you can maybe click on to see how it works, because there is no official published link. And I also was talking with the customer that I can share it. So,
Perfect. Okay. And if there is not a direct further question, So first of all, from my side, I think was a quite interesting session here. From different perspectives, from modeling towards battery recycling, towards an industrial view on the topic. And I'm quite glad that we had a lot of people staying inside our spotlight talk till the end. About the future perspective, I think they did not change very much, but what came in is a little bit more the digitalization aspect. We see a trend from my point of view in the last recent years, at least towards circular economy and urban mining, which increased. And therefore also the environmental focus, because we got some European regulations and we need to think about our solvents and closed loop systems. And therefore also coupling with electrowinning membranes and crystallization becomes into focus. There's yet another question popping up, or not? Oh no, I just went to the wrong view. What I think about the EFCE spotlight talks, these are excellent possibilities to share actually the knowledge on a broad range without traveling too much. So keeping CO2 amount low actually. And I see the EFCE in this way, even so as an international network. So please feel also free to contact us via email, via LinkedIn, or just directly on conferences or wherever you see us. Or maybe you can write an email to Martin Prue or myself or Boelo, for example. Boelo, do you want to add something to this?
Yes, thank you very much. For me, this was a spotlight talk that is in the heart of where my own research group is working at. So it was very interesting to see. But this is just one of the many spotlight talks we have, and I'm really happy with how it went today and with the last week. So thank you all for watching, and if you are not able, or if you were not able to follow all of the talks in a few weeks from now, they will be on the YouTube channel of the EFCE. And of course, indeed, you can contact me via email, via LinkedIn, or I hope to see you at one of the future EFCE events. And next to the EFCE event in Lisbon, there are some upcoming events specifically on liquid extraction. I will not travel to Melbourne this year, unfortunately. I would have loved to go. But in 25 to 27 of February, there's another extraction event, and we aim to have this a European event. So the language is English. This is not it is organized by the German extraction community, chaired by Professor Andreas Jupke from Aachen. But we really intend to have a wider outreach and to have more international participation in these events. So if you are interested in coming to Germany for an in-person meeting on liquid extraction, please put 25 to 27 of February 26 in your calendar. That said, thanks a lot, Mark, and also Andreas Jupke, who is not live in the meeting, but he was instrumental also in getting together Lukas and Daniel and Alexander. And thank you once again, Martina, for hosting all of the Spotlight talks and this one also. With that, I will close this session. Thanks for watching.